Testing. I think this way is the largest. If I go full screen, then the other icon will cover it. So other people joining the class from different group. So I leave it in this way, okay? Good afternoon, welcome back. Welcome back to the second last lecture in this semester. So my plan for this week would be finish up the last topic. Hopefully I've done it within this lecture. And if we manage to finish it, then next week we will just left with last tutorial and then some revision, recap, summary of what we did after midterm. And then we will have some review question. We can do it together. And then discuss about the quiz. Okay, that's the plan for next week. And how fruitful is next week should be depend on you. So there will be 1 hour for you to ask me question. Okay. So you can we can discuss any question you like. Okay. Any problem you met during your revision. Okay. Any questions? Anything? Very good. Okay. So last week we finished on trees, and today we will start on the topics Boolean algebra, which I promised you in the very first few lectures. Okay. So this is a wrap up for what we did this semester. So what's the Boolean algebra? So Boolean algebra should be a generalization of proposition theory, set theory. Okay. And then we will see soon lattice is also a Boolean algebra. So let's introduce the definition of Boolean algebra. So first of all, okay, it is a set. Okay, so you should ask what are the elements in the set? So they are just bunch of variables. Okay. So you imagine there's a set B, okay, and then there are two binary operations. Okay. One of them you can remember as the OR and AND. Okay. Cat OR and AND. Or sometimes we will prefer to use plus and multiplication. Okay. Or and intersect union addition multiplication. Okay. Two of these. A pair, come with a pair. And then we got the elements 0 and 1 in the set. Okay. Oh, okay. And then one more operation is the unary operation. So unary mean one, university mean all the different things joined together. So uni is one. Pi is two, uni is one. Okay. So what thing they have to satisfy? So the first thing you need to satisfy is S cup 0 is X, and then X cap 1 is X. Okay. So these are the familiar identities law. So you can think of a number plus 0 is always the number. A number times 1 is also the number. Okay, you can understand it in this way. Okay. And then the next one is the inverse exists. So X or S bar is 1 X bar. Okay, so this is called the complement law. Right, remember, true or false is always true and false is false. Okay, so this is the generalization. And then the next is the associativity. There's associativity on the cap and also the cup. So these are associated. So you can combine the left first, or you can combine the right first. They are the same. Okay. So there's no ambiguity of writing X or uh, there's no ambiguity of writing S or Y or Z. Okay, because you can combine the right first or you combine the left first is the same. Okay. So this is well defined. Okay. Next is the commutative. So A intersect B is the same as B intersect A. X union Y is equal to Y intersect X. Or X intersect Y is equal to Y intersect X. So these are the commutative. So, and then the last one is the distributive law. Hope you still remember this, okay? So just to remind you, the example we did on the very first week. So we did the positional logic. Okay, inside the propositional logic, what are the things we care? So they are the true or false element, true or false proposition, right? So it's a true, it's true, this is true, that's false. Okay, tautology or contradiction. And then the proposition, we write PQR, remember? And then we can take the or and n, right? We can take or, P or Q, what we call that, disjunction or the conjunction or proposition, right? And then we also can have the, what do you call it? The negation of the proposition, okay? So the claim is this is the algebra, okay? Remember the long list that we have last time? The long list of formula in the proposition, right? You keep asking me whether I need to remember or not. So those comprise uh, all the laws here, right? Okay, so we need this law to hold, so that it is a Boolean algebra. Second, we also see that in set theory, the set also satisfies similar property, right? Have the same tables. Okay, so in set theory, we also have 0, 1. 0 is the empty set, and then 1 is the universal set. And all the different sets. Okay. And what else do we have? We have intersection. We have and we have union of set and intersection of set. Okay. And then what bar operation we have here? Here is the negation. Here we can take the complement. Okay. Can take the complement of set. And then we also have the long list of formula, right, for set theory. Okay, those lists also contain these laws. So Boolean algebra is a set theory is a Boolean algebra. Okay. Third one, surprisingly, we just finished studying the graph and theory, right? Graph and trees, sorry, graph and trees. So surprisingly, you can show that lattice also satisfy the Boolean algebra. Okay, so you may think of how to combine 2 points on the lattice. Right? So how to combine the 2 points on the lattice? So what are the 0 and 1 in this lattice? Right? So can you think of one way to combine the lattice? So give you 2 lattice, how do you generate another lattice? What kind of operation you can take? This is what you learned before, huh? Huh? Plus. Plus. So how do you add 2 at lattice? How do you add? Like how in the lattice, right? So you can imagine any lattice you like. So how do you add 2 lattice and then give you another lattice? Any idea? Any idea? I promise it's what you learned before. Use what you have learned before. Idea. So how if I give you two lattice point, how you generate another lattice? Idea. Idea. Give you two lattice point, how you generate another lattice point? Idea. Lattice is what? Is a what set is it? What ordering you have on lattice? Huh? Yes, partial ordering is a pole set. Okay. So in pole set, we can find what? Maximum, minimum, upper bound, lower bound, right? Okay. So given 2 points, you can consider the greatest lower bound of them. Okay. You can consider a greatest lower bound. You also can consider the lowest upper bound. So you regard the 2 point as a subset of the lattice. Yeah. So in this case, the zero here will become the not wrong, it's the least element. And then one is the greatest. Okay. Of course, this is not trivial. You have to show it. This actually satisfy this 1, 2, 3, 4, 5 laws here. Okay. You need to show that with this definition, when you compute all these, they are correct. They are true. Okay. And then uh, so for the bar operation, you need to consider, you need to find the element such that these two equations here hold. Okay. You need to find what's this element. This will become the bar operation. If you're interested, textbook, I think they got it. They have it. But what you need to know for now is lattice also a Boolean algebra. Lattice is also a Boolean algebra. Okay. So how you combine the two elements, you take the G greatest lower bound, or you can take the lowest upper bound. Okay. So kind of take everything together. Okay. So the next one is just to remind you this table here. So remember this table here? I gave it to you in the exam one. Okay. But this is the generalization of it. Okay. So we have all these. Not that just now Boolean algebra only have how many laws? Only have 5 laws, right? But here got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 laws. Okay. So this means all the others law can be derived from these 5 laws. Okay. Abstractly. Whether you are in any theory. Okay. We will have question on this type of question in the tutorial. I think the tutorial will happen next week. That question. This week we're still on trees tutorial. Okay. So abstractly we can prove this without speaking of proposition, without speaking of set. As long as they satisfy this 1, 2, 1, 2, 3, 4, 5 laws, we can derive all the others laws. Okay. Without knowing what exactly the algebra is, as long as they satisfy that laws. Okay. So this is the power of abstract algebra. Okay, next. Okay, next, we will study the Boolean function. So let B be the set of 0 and 1. Okay. And would be the n tuples of 0 and 1, where we denote as S1, S2, up to Sn, such that xi is in B for all of them, is the set of all possible n tuples 0 and 1. Okay. And then we will call the variable x bin variable if it assumes values only from B. Okay, only from, so it can only take values 0 or 1. If the variable only can take values 0 or 1, we call it a Boolean variable. Okay. Function from DMT is function of degree n. Okay. So a Boolean function is taking n variable, n input, output, one output. Okay. And take in n input and output one output. Okay. This is Boolean function. Okay. So next definition is the Boolean expression. Okay. So Boolean expression is made out of 0, 1, and all different variables. Okay. So can be defined recursively. So for example, 0 is a Boolean expression. 1 is also a Boolean expression. X1 up to Sn are all Boolean expression. And also if you got two Boolean expression, what you can do is you can take the bar operation. Okay. So you can, if it is in the case of proposition, you take the negation. If in the setting, you will take the complement. Okay. So you can take complement, or you can multiply the two Boolean expression, or you can add them together. Boolean expression. Okay, I think some of you maybe were confused of what I'm talking about. So maybe let me just show you. So for example, we can write x plus y, or we can write 0, we can write 1, or we can write x plus y times 1, or we can do x times y plus 1. Okay, so these are all Boolean expressions. Any question about it? No. So this variable can take in 0 or 1. Okay. So actually these are functions. So let me put a remark first and then I will say more. So each Boolean expression represent a function. Boolean function. Okay. So for example, x plus y. X plus y is actually a function from b2 to b. Okay, because we can write it as fxy equal to x plus y. Okay, so for example, if I take x equal to 0, y equals to 1, f01 is what? What is f01? 1. 0 plus 1. What's 0 plus 1? 1. Okay. Okay. So take in two values and then give you one value. This is what Boolean function did. So yeah. So makes sense. Each Boolean expression represents a Boolean function. So in this case, you can see here we can add Boolean expression, right? We also can multiply Boolean expression, right? We also can take complement of Boolean expression. So Boolean function itself become a we can plus, we can multiply, we can take complement. So Boolean function itself, the set become a algebra. Okay. Because algebra, you just need two operation plus the bar operation. But of course, you need to satisfy the law. Okay. So here, what we have here is the Boolean algebra of Boolean function. Okay. Because we can add expression, we can multiply expression, we can take bar operation. Okay. So in this case, what time is it? So in this case, we can talk about when two Boolean functions are the same. Okay. Or when are they equivalent? When the Boolean expression are equivalent. And we also can talk about complement of a Boolean function. We also can talk about the Boolean sum of the Boolean function. I put BF. And then we also can talk about the Boolean product of Boolean function. Okay. 4:30. Let me see how we finish. Okay, let's keep going first. Okay. So from the Boolean function, we can build another algebra using Boolean function. Okay, make sense? So when are two Boolean functions the same? Okay. So when are two functions the same? Okay. Let me ask you, when are two the when two functions are the same? Okay. Huh? Any idea? Huh? When the object and the image are the same. So if you input the same, when you input the same domain, same element in the domain, you should get the same output. Okay. So here is also the same. So if you have two Boolean variables, functions, okay, they are equal if and only if they equal on the value when you substitute any domain, any element in the domain. Okay. For all B1, B2 up to Bn in B. Okay. So let's see, for example, what? Okay. So for example, these two functions here. One is x plus y times z bar, And then the other one is x, y, z bar plus x, y bar, z bar plus x bar, y, z bar. I claim that these two are the same. Okay. Can you see why they are the same? I think it's not just multiplication. So you need to check. So you need to check the truth value table. Okay. So you need to make sure that every value they take, they give the same output. Okay. So I got this table. Got the table here. Table here. So you can go and compute the output of this and then compare with the output of this. Okay, if they are the same, then they are the same function. Okay. Okay. So you need to compute the output here. Okay, so here already got the output, but you need to read about this. So for example, x, y, z bar, right? So x, y, z bar, x, y, z bar only get once at this spot here. So it is all zero at the other spot. Okay, and then x, y bar, z bar, x, y bar, z bar only get one here. Okay, and then x bar, y, z bar only get one. Okay. But this one is just a quick way, but you need to like try and work it out, the output for G. Okay. Yeah, you need to work it out. Okay. Work out the output for G and then see that it agree with F. Just now it's just a quick way to see it. Make sense? Okay. So you need to use G. Okay. So actually these two have a relation is what we call the sum of product expansion. So if you want to look at your textbook, actually G is called the sum of products expansion of F. And this is in the 12.2 section. So you can see that here are the terms here are all the products, and then you take sum of them. So sum of products expansion. Okay, but here is not. Here is just some products. Okay. I mean, this is not immediate if you haven't tried the compute the output here. You need to compute the output of G and then compare with F. Okay. But later we will develop this technique more. You will see it maybe easier later. Okay. But for now, you should work out the output of G as well to help yourself. Hey, next, how about two equivalent Boolean expression? Okay. So if the two different Boolean expression represent the same function, okay, then we will say that they are equal, okay, equivalent. So in this case, for example, what we have, for example, xy is equivalent to xy plus 0, okay, is equivalent to xy times 1. Okay, so these are all equivalent. Okay. All these are equivalent because they represent the same function. Next, how to take complement of the Boolean function. Okay. So how you take the complement of Boolean function is just to take the complement of your Boolean. So the function f bar is defined by bar on the in bar on the Boolean. Okay. So if you don't get what I said, for example, f x equal to x, okay, then what is f bar x? F bar x is just equal to in bar on the Boolean expression. Okay. Okay. Good. Yeah. Next. Next. Suppose you have two Boolean function. Just now we already have the expression, have the sum of Boolean expression and the product of Boolean expression, right? So this is exactly how we define the Boolean sum and the Boolean product. Okay. So just to take the Boolean sum f plus g and the Boolean product fg, what you do, you just multiply, you just add or multiply their Boolean expression. Okay. You could add the expression and you can multiply the expression. This is how we define the sum and the product of the Boolean expression. Okay, make sense? Okay. So why this define a Boolean algebra? You should check that they satisfy the 5 laws using this definition. Okay. I told you how they combine and then tell you how to take the complement. Then you should check the 5 laws. If you check the 5 laws, then this will become an algebra. This algebra of Boolean function will become the Boolean algebra. Okay. Typical algebra just have 2 operations, plus and multiply. For example, um, what? For example, real number is an algebra. Matrices is also an algebra. N by N matrix. Yeah. Okay. Boolean algebra is special because you have this complement operation. And then need to satisfy the 5 special laws. Okay. Question? Any question? Let's talk about logic gate first before we correct. So next is logic gate. Okay, so we come back to logic gate again. So last time I think we also briefly introduced logic gate, when we touch about the OR gate and gate inverter gate. Okay. Just to remind you again. So Boolean algebra actually is used to model the circuit circuitry circuitry of electronic devices, where the basic elements are called the gate. Last time we briefly go through this. Let's look at some example of the gate just to remind you. Okay. So what we have here is the inverter gate. Again, taking the bar operation deviation, right? Remember last time. X p equal p and then become not p. Okay. So after generalize, we become a x bar. X y we can add them together is an OR gate, or we can have an AND gate. We can multiply them. Okay. So examples of circuit. So you can combine different circuit together, okay, and then produce one output. You can see that these two output actually the same, okay? But you can see that the design of the circuit is different here. So our goal is to increase efficiency. So we want to use as fewer gate as possible to produce the same output. Okay? So for example, maybe we will use this one, for example. Okay? Or maybe I think we will use this one. Yeah, this one, because that's only taking 2, but this one taking 4. Or depends on the situation. Maybe you need to have 4 sometimes. Okay. Okay. So there are different way. I think we also did it in the first few class. We see different way can get the same result. And so for example, you can go more complex. So you can go through some examples, some more examples, and there's adders in the textbook. You can go and read about it, but we won't talk about it, and it's not important for the exam. It's just a small part. You can read about it, adders. I'm not sure what's the use of it, but you can read about it. And okay, maybe any question? Any question before we have a break? We take a break until 4:55, and then we'll continue the next section. Yeah. 来，什么叫看不出来？它是有一个例题，然后你说它是什么样的题？给我看，给我看，给我看。是要看电脑，所以我们有带我妈的嘛？啊？我们有床，懂吗？是这种。有是有啊，可以有，可以有。我们上课的话，就只是 and or 还有 not，对吧？上课刚才讲了，因为刚才你讲有 not or 还有 and 嘛，这样我们之后有选还是有些我们这种。不用在这一课，有这个东西不用在这一课。 还没不用在我的话。
对，就是这样的图，是吧？
呀，然后，
你说它是等价关系，
等价，什么叫等价关系
就是 equivalent
？equivalence relation 啊，OK，然后
它那个传递性怎么看出来的？
传递性你只要降就降嘛，
这样就传递了。
哎，
这不是那个吗？这是传递性，这我觉得这是那个对称性。
对呀，因为它这里最大就是它
这是传递，这可能是对称的，不一定传递。
也算啊，你看 A 嘛，也是传递啊，听明白？听明白？那个 C 可以是 A 啊，
当然，这个一个点代表的是 A，这个点代表是 B，然后代表从 A 传到 B，再传到 A，所以代表它有 AB，然后也有一个 BA，然后一个 A。
A 是那个 loop，它只是比较小，啊，他只是说 A 要在里面嘛，
对，它为什么要
但是如果它没有这个 loop 的话就没有了，如果就这样罢了就没有了，
如果它是有两根的，
什么叫两根？
两根所以没有什么意义。
什么两根？
它当时说这样两点
对
这样的东西，
对，
这个整个就没有什么用。
它那一边也要符合 transitive。对，如果其中一边的一个 loop 不见掉就不 transitive，如果这边没有 loop 的话就没有了，就是我下来上去，但那边没有东西。
写了一个传递性什么从零推到一那个什么，
没错，
写了一个什么 if 那样。
我忘记了，我在哪里写？
刚在哪里写啊？我也忘记了。
我也忘记什么了，我忘记你
再见。如果
也
然后从这个如果可以是你可是能推出来整个你喜欢是也是你啊？
给我看一下，
找一下。
那给我看一下呀，
因为一个 definitive 方去找还没有正 circuit 跟
没有
没有，
那个
没有，
那你会不会错？
会出现 example 这样子吧，
这一定可以做出来用那个 theory。
也
OK，你不会，
可能不会怪怪的，不会怪怪的。
而且也是不会。
我是应该说
你是讲 final 还是
我讲
等一
quiz
下
的 final，
对，
开 final 会
但是不是难啊
final 会是 proof，
？final 我忘记了，好像有，但是不是很难，不是很特别，
我是应该说什么？
不是
会做 proofing，
不是那种啦，不是那种，
什么不是很特别？
不是那种玩来玩去的。
做 proofing，
没有，我是讲不是这种啊，不是这么深，是普通的吧？definition 吧，就是 checking definition 这样。
A
think
is not
something
maximum
is 什么这样？
plus，
哎something like that 啦，就是
A is not
这个东
maximum
西我错了是
或者 proof 一些 property 而已，没有那种特别的，那种
not inductive。
啊，没有那种这样特别。
这个所以是什么意思？我记错了，是这样的，这个
这个干嘛？
没有，这是什么意思？
因为它的条件是 A taller than B 嘛，对不对？但是如果你有这个条件的话，你就不会有这个条件了。你不可能 A 比 B 高，B 又比 A
但是这样不也是整个命题也是对的呀？
错
啊，这个 if 是这里是错的，
啊，那这个
这个
你的对哦，
那
所以
能说明什么？
所以它就符合这个 anti symmetry。
所以它就有非对称性。
对，
非对称性是这个命题为征，就是对。对我能不能换个角度理解？就非对称就是我这个关系集合里面不会出现 AB 和 BA，被他们生的，我可不可以这么理解？其实就是这个意思。
再来一次。
就是我的关系里面不会出现 AB 和 BA。 然后除非 A、B 相等，这样来判断它，可以吗？
然后但是这里相等也不存在哦。我不知道你要讲。
啊，我就讲判断，我判断这个它不非对称，因为不可能 A 比 B 高，B 又
然后呢
B 又比 A
然后
高，
呢？
所以它非对称，可以吗？
所以呢？要，
所以它非对称，所以它是 anti-symmetry。
可以，
可以，
对呀，
可以，这个意思。
就是这个意思。但是我不知道你要讲什么，他是你讲的东西是他讲的，但是我不知道你。
我的意思是证明这个，证明
对
anti-symmetry
对
就是写因为 A B，就是因为
这个条件不符合嘛，所以
所以
对
整个
对，因为就是只要这个不符合的，
但这个 anti-symmetry 不是跟这个完全相等的判断条件，
是啊，
完全相等，等价于这个判断条件。
是啊，它定义。
那我那个跟这个应该不等价呀？
你的那个是哪一个？为什么的？
把这个挪到前面去，就是
我不知道你在干嘛。你讲的东西不是你想的东西。
假说它是 anti-symmetry，
可以
然后我说因为
嗯
A 比 B 大
嗯哼
，B A 比 B 大的时候，B 不会比 A
对
，A 比 B 高的时候，B 不会
对，
比 A 高，然后就所以它是 anti-symmetry。
但是你要知道原因为什么？
原因，我觉得那个就是原因。那写可以吗？那我
可以，但是问题是这个就比较严谨啊，就是透过 definition。
这么写比较严谨，
Yes，
所以我要在说它是 anti-symmetry 的时候，我是不是要这么写？
你应该是说没有一个人可以同时符合这两个条件，没有一个人会同时符合这个条件
没有两个人
啊？
是没有两个人，
没有两个人啊？对，没有两个人可以符合这两个呀，
所以它是 anti。
没有两个呀，没有两个人，没有人啊，一个人也可以，那两个人可以是相等，
两个人可以
可以 A 吗？
对对对
呀，但是也不符合，你看 reflexive 也是错的。
对对对。怪
哎，我忘记问你，你头发是不是剪这样短？剪错了。
还好，也算是吧。第一次剪完，然后不太习惯，看着不太顺眼，第二天去剪。
又去剪啊？我以为你准备出家。
就这样。
嗯，
对，其他应该没什么。
OK，
我好像还有一个，
哪一个？
我好像刚才看了一眼，我不太记得。
我要开始啊。先开始。
你充电好不好？
你要坐这里，叫你坐这里。
真的可以，长时间。
Okay, just now, the online participant point out one point here. Yeah, here I think I wrote something wrong here. So here, it's just the N. Huh? Yes. Oh, you already saw it just now? Then why not you point it out just now? Yeah, I should point out just now. Yeah, here there's a typo here. Okay, so when we talk about associative, we always talk about the same operator. Okay, so you can take all or you can take n. Okay, associative on the same operation. If different operation, we will have a distributive law. Okay, n or and n or n or. Okay. Okay. Good. Next, what's next? Okay, so just now we talked about gates, right? Okay. So we see that one output we can have a different combination of gate. So next we will learn two algorithm. Okay. So the two algorithm we will learn will be to minimize the gate we use. Okay. I was thinking, should I write or should I just show you? 6. I think we have enough time. Maybe I just write that. Okay. Let me see. Okay. So next topic is 7.3 minimization of gate. Minimization of circuit. Okay, so this is to increase the efficiency of circuit. And maybe can reduce cost. Okay, so let me give you one example. The textbook. Okay, so you can see this example here. Okay, we can have 4 gates to produce this output here, a single output here. Okay, and we have 1 gate to produce a single output here. But it turns out that these two are actually the same. So why are they the same? So let's look at the first Boolean expression here. Okay. So when you add them together, you can factorize the y and y plus y bar using the distributive law. Okay, you can use the distributive law, or you can commute it first and then distribute it up to you. But first use the distributive law. Then y plus y bar. Okay, how you imagine this? True or false is always true. Okay, so 1. Well, 1 is true, right? So P or not P is a true. Is 1 true. Okay, what we call it? Tautology. Yeah, tautology. Yeah. So it's always 1. So you can get rid of y plus y naught. So it's actually exact. So instead of using 4 of these, you can just consider this. Make sense? Okay. So now we want to build algorithm to see this instead of just playing around with the algebra. Of course, you can do algebra way, but we will use a more systematic way to it. Yep, makes sense. Let's write something here. Okay, so what we will learn today, the new thing you will learn is called a Carnot map. Okay, or we call it chair map. Carnot map. This is the first algorithm. The second algorithm is not too far different from this. It's just using different description. So you have to understand this algorithm first, and then later we will see the second algorithm. So the first algorithm is called the Carnot map. So what's a Carnot map or a care map? So a care map for a Boolean function. Okay. A Boolean function is made out of Boolean expression. In n variable consists of 2 to the power n cell. Okay. So for Boolean function in degree n, you need to have n cell. And then what this cell do is you will put in one. Oh, wait. Can we step back first? Can we step back? Step back. Step back. Step back. Step back. I forgot to introduce one more terminology. Step back. Step back. Okay, so yeah, step back first. So let's introduce some more terminology. So one thing is we call the literal. Okay, so literal means it is a Boolean algebra, Boolean variable or its complement. Okay, so why we need to introduce literal? Because we not only care about Boolean variable x, y, z, we also care about its complement, x, x bar, xi, y, y bar, z, z bar. Okay, these are all literal. Okay, maybe I put the example here. X, x bar, y, y bar. Okay, these are all literal. We care about the complement. And then next is called the min term. Okay, so min term is the product of these literal. So the min term, minimum term, min term of Boolean variables, and is a Boolean product. Okay, just now we introduced the Boolean product, right? So you just multiply yi up to yn, such that all of these are the literal. Or yeah, or I can say where yi are literal. Okay, so min term, hence min term is a product of n literal. Okay. Okay, makes sense. So okay, let me just give another example then. Maybe you have x, y, x bar. Okay, is a min term. Y, y bar is a min term. Okay. So literal and min term, minimum term. So okay, so let's come back here. So you can see that an Boolean expression is can be made out of, like for just now. Okay, let's go back to the picture just now. So where's the graph? Okay, you can see here. So here is the min term. Okay, so product of literal. Okay, sum of min term. Make sense? Okay, so min terms, literal, 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 literal. Okay, so you can see that the Boolean functions are the sum of min terms. Or Boolean expression, they are equivalent. And let's move back again. Where is it? Okay, so K-met for a Boolean function, or Boolean function is also a Boolean expression, right? In these n variables consists of 2 to the power n cells. You need to build 2 to the power n cells. And then I haven't tell you how to build. I just say there's 2 to the power n cell first. And then where you can put one, okay, you put one in the cell if you have the min term exists in your expansion. Min term presenting if this min term. Okay, I think I saw someone typing in the chat again. Let me check the chat. Let's see, got question from the online. Mind blown, law. LTS nothing. Okay, never mind. Nothing. Okay. I don't know what's mind blown. Okay, never mind. Okay. Okay. And then the next one we will tell about adjacent cell. Okay, so cells to be adjacent if the mean that they represent, okay, differ in exactly one literal. Or we will say that the cells are adjacent when they are differ by one literal. Okay, let's see an example of K-map. Okay. So for example, we need to start with one function, right? So for example, let's start with x y bar plus x bar y plus x bar y bar. Okay. So how many variables do we have here? Two. Okay, x and y, and they are literal. Okay, they are complement. So there are two variables here. How many cells do we have? 2 to the power n. So what do you what do you get? 2 to the power 2. Huh? So 2 here, 2 to the power 2. How many cells do you get? 4. Okay. So you need to create 4 cells here. Okay. So these 4 cells will correspond to x, xy, xy bar, x bar y, and x bar y bar. Right? Make sense? Okay. So the K-map just now says put 1 in the cell representing a min term if this min term is present in the expression. So how many min term as present here? How many cells? And how many min term? How many min term present in the expansion? 3, right? So xy bar, you got xy bar, you got s bar y bar, yeah, s bar y bar and x bar y. Okay, so you put 1 in these 3 steps. Make sense? Okay. 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 So you can see that which 2 cells are adjacent. Okay. So these 2 cells are adjacent because they are differ by y, right? Because their x is the same, so they are adjacent. How about these two? These two are adjacent because they are differ in x or y. X, right? Because this one is xy, this one is x bar y. Okay, they differ in one literal. Okay, and these 2 cells are adjacent. Why? They differ in what literal? Right, because here s bar y, here s bar y bar. Okay, differ by 1. So, have we discussed this? So here are adjacent because they differ in x. Yeah, makes sense. So these are adjacent. So make sure when you draw, right, you have to draw adjacent. You have to put the right adjacent literal. Later we will see. When we go into higher dimension, then this one will become more important. Low dimension, you split right or left, up and down, they're still adjacent. Okay. Next. So next we will speak about the algorithm. Okay, let us don't spend time to write the algorithm, but we go to the algorithm and then try to study some. Okay, so the algorithm is, so the algorithm for the K-map minimization method is first you build a K-maps, okay, what we did just now. So in different variable, 2, 3, 4, up to forever. And identify, second step, you need to identify this is the key. This is the key. Identify the largest possible blocks to cover all the ones with the fewer blocks using the largest block. Okay. So your goal is to create blocks to cover all the ones. Okay, you can try to imagine first, later I will show you. And then the min term can be combined based on the available blocks and the corresponding sum of product is 4. Okay. So you can try imagine, then later I will show you now. So for example, in two variables, right? Okay, two variables, you have how many cells? You got 4 cells. So what are the possible blocks you could have? Okay. You can have, of course, the simplest one is a block of 1. Okay. So the simplest case is a block of 1. So for example, y bar. So if you only have 1, of course, the simplest form is just xy, right? You can't go any more simpler, right? Okay, so this is the simplest one. And you already covered it. Okay. But let's say you have 2 ones here. Okay. You can form a block by covering these 2. Okay. You can form blocks, rectangular blocks or square blocks. Okay. You cannot form something like this. Okay. This is not allowed. You can only form rectangular blocks. Okay. Rectangular include square. Okay. You can form rectangular blocks. Okay. So why can we combine these two? Remember just now we see that we can factorize. So what are these two min term here? Okay, can anyone recognize the min term existed here? What is this min term here? What's this min term representing? X, Y, and then this one, X bar Y. Okay, so when you add these two, they are differ by 1 because they are differ by 1 literal because they are adjacent. So you can do what we did just now. You can use the distributive law, right? Okay. So when you add them, this is 1 times y is equal to 1. Okay, so that you can combine them. So there's one way to combine them. There's another horizontal way to combine it. Okay, using the similar logic here. Okay. And then next is there's one more cases you could have is you have a block of 4. Block of 4 cell here. Okay. So when you combine all the possibilities, what you get? You combine all the possibilities, you will always get 1. Because you already combined all the possibilities. Really sum all the possibilities off. Okay. If you don't believe it, you also can use this method to calculate something. Maybe if you want, we can try. So this one is x plus y bar plus x bar y plus y bar. So y plus y bar is what? It's 1, right? So it's 1 plus x bar times 1 is equal to x plus x bar is still 1. Okay. If you still don't believe it, you go and build the truth table. Okay. And then you will see that it's always 1, 1, 1. Okay. There's a lot of ways to check it. And then next, how about this one? Just now we did, is this what we did? Yeah. Just now we did this example here, right? Okay. So for this, we already said that the block cannot be non-rectangular. Okay. Must be rectangular. So you only have 2 rectangular to cover the one here. Okay. So what you can do is you can combine these 2 blocks and then combine these 2 blocks to cover all the one here. Okay. So if you just do one, if you just do one block here, you haven't covered this, then you won't be able to minimize this circuit here. You need to minimize all the block that covers all the one. Okay, and then use the fewest block. Make sense? Okay. So what you do here is you combine these two. When you combine these two, what do you get? What do you get? What's the mean term you get by combining these two? What's the mean term you get combining SY bar and S bar Y bar? Y bar. Okay, so you get Y bar. How about this one? S bar. Okay, so what you get is S bar plus Y bar. Okay, so if you have some doubt, you can go form these two truth tables. They will have the same output with the same input. Okay. Okay, so for variable 2, in two variables, block of adjacent cells, okay, can combine into a term of one literal. Okay, for adjacent cell, you can reduce to one literal. And then if you have a block of all the 4 cells, you can combine into one. So in this case, 4, and then combine into 1. This is for just to warning you, this is for this is for 2 variable case. Okay, so let's look at 3 variable. Okay, so in 3 variable, more combination we can do, right? So we can have block of 2, block of 4. Again, there's 2 ways to do block of 4. So in 3 variable, how many cells do you have? What do you reckon? How many cells? 2 to the power 3 is 8. Okay, so 8 cell, you can imagine you can draw it like this. Okay, so you can do it block of 4 like this. You also can do it block of 4 like this, right? Okay, so or something like that. Anyway, so yeah, so they correspond to different mean terms. Okay? Okay, let's look at example here. So for example, okay, you can see again. I want you to note something special here. You can see that we place x, y bar, z bar here instead of y bar, z here. Okay, because we want these two differ by one literal. Okay, if we place y bar z here, then these two will differ by 2 literal. Correct? Yeah, correct. Okay. So adjacent cell only can differ by 1 literal. No matter how you place it, but you need to measure on this. And also you need to make sure the last and the first one also differ by 1 literal. So it's like going a cycle here. So these two are adjacent, these two are adjacent, these two are adjacent. The first and the last one is also adjacent. Okay. No matter how you place it, you need to measure this rule. Otherwise, it will be hard for you to use this algorithm here. Okay. So in this 3 variables way, you can see that we can combine the 2 cells like this or like that. Okay. So when you combine the 2 cells, you will left with product of 2 literal. So you reduce by 1. Like just now, 2 literal become 1 literal. Okay. Now 3 literal become 2 literal. And then when you combine block of 4 in a square, you will get 1 literal. Or block of 4 in a rectangular form, you will get also 1 literal. If you combine all of them, that means you get the whole possibility. You get everything. 1. Okay. Makes sense. So you can imagine you could have 4, 16, 2 to the power 4, 2 to the 5, 2 to the power 6. Okay, you can draw your own cell. Okay, yeah. Any question on how to reduce this? Any question? Anything you want to ask? How to reduce? Is this like magic or not? Huh? Okay. Huh? What's that magic? Oh. Wow. The online participants so active one. Okay. Okay, next. So yeah, okay. So next. When we go into higher variable, the following concept will be important. So, okay. So there are 3 concepts here we want to touch on. So first we call implicant. Okay. So what's the implicant? So just now we have the mean term that reduced by the block, right? Red again. Okay. So actually those we call it a literal. So the simplified mean term we get from the block is what we call the implicant. Okay. Implicant of the function being minimized. So let's go back to the example here. So what we call an implicant are what we call the implicant. Okay. So these are what we call the implicant. Okay. What's going on? Okay. So the product of literals correspond to a block of all ones in the K-mat is what we call the implicant of the function being minimized. Okay. So you see that these are minimized of the right hand side. Okay. Okay. Next one is what we call the prime implicant. Okay. So it is called prime implicant if this block of 1 is not contained in a larger block of 1. Okay, so you can imagine that sometimes we will have overlapping block. Okay, so if it is not overlapped by the other block, we will call it a prime implicant. And this. So the final one, we will call it the essential prime implicant if this block of 1 is the only largest people. On the K-mat. Okay, so maybe I show you the example of this, the prime implicant and essential implicant. So for example, use K-map to minimize this sum of product expansion. Okay. So you should imagine that in your mind, there's one logic gate behind this expression here. Okay. So you need to use some inverter and then use some AND gate, use some OR gate to produce this. Okay. So you can see that there's a lot of gate you need to use here. Okay. So we want to try to minimize it using the K-map. Okay. So what you do, you form the K-map first. Okay. Here, how many variables do you have in this tree question here? X, Y, Z. 3. Okay. So 2 to the power 3. So you should have 8 cells. Okay. So these are the X cells corresponding to the K-map here. And then you place 1 whenever you have the minterm in the expansion. Okay. So you have 4 here, 4 minterms here, so you have 4 ones here. You have 5 minterms here, so you have 5 ones here. And then 1, 2, 3, 4, 5, 6, 7. So you put 7 ones, and then 4 ones. Okay. And then what you do next is you draw the blocks, rectangular blocks. Okay, rectangular blocks. Okay, so just to remind you that the last one and the first one is always adjacent. Okay, so you should draw another block. Okay, draw all the blocks you have, and then based on these blocks, you minimize it. Okay, so should we learn how to minimize first, or should we learn how to see essential prime first? Okay, let's see how to see essential prime and prime first. Okay, so implicants refer to the minterms after minimization. Okay, and then what do you call a prime implicant is if you have a block, okay, not contained in a larger block, you will call it a prime. So for example, let's say for example, I just make up myself. Okay, so let's say we got one block here. Okay, but this block here is contained in a larger block here. Okay, then this is not a prime. Okay, so to be a prime, it must be not contained in a larger block. Okay, so for example, here is a prime. Okay, this here is a prime because it doesn't contain a larger block. Okay, so what's the difference between prime and essential prime? Okay, so essential prime means you contain a 1 that is not covered by other block. Can you see it? So why are these essential prime? They have 1 that's not covered by other block. This prime implicance here is not essential because both 1 here is covered by different block. Make sense? Make sense? Following? Following. Prime and essential prime. Any question? Huh? Yeah. Yeah, take other example. Which example you want to ask? Huh? A, B, C, D, which one? Oh, huh? Oh, too greedy, Too greedy. Pick one first, Max should be greedy. I mean, yeah, you can learn more, but now I can only do a few. Pick one first, and then we will decide whether it's prime. Huh? A, okay. So which one you want? This one, this one, this one. You mean this one? Okay. So this is the implicant. Okay. So there's an implicant correspond to this. So is this a prime implicant or is it an essential prime implicant? Okay. So is it a prime implicant? Yes or no? Yes, because this block of 1 is not contained in a larger block. Right? So this is an implicant. Is this essential prime implicant? Yes, because it's the only largest possible block that contains it. So for example, when is this not a prime implicant? So it is not a prime implicant if there's another block containing. Okay, then this is not a prime implicant. Okay, makes sense? Okay. Yeah. So yeah. Okay. Any more question on this essential and prime? So why we introduce this essential and prime? Because we don't want to take too many min term. Okay, we only need the smallest possible number of block that covers one. Okay, for example, you can see that there's 3 blocks that cover this one. So which one should we take? Should we take it all? This will become a question. Okay. We'll see it in a later question, I think. Okay. Yeah. Okay. So okay, let's come back on how to minimize this expansion. So after we get this block here, and then we already draw all the blocks, possible blocks, right? So what you do is see this. Okay, online participants say makes sense. Okay. Okay, next, so for part A, for example, we need to include all the blocks that contain 1. Okay, so that means we need to check for all these blocks. Okay. So first, this is the implicant. This is the only implicant. So this implicant is S bar YZ. Okay, so you got this term here. And then when you combine these two, these are adjacent cells. They are differ by Y. Okay. So when you combine this block, what do you get? You get X times Z bar. Make sense? Make sense? Make sense? Others? Okay. So if you don't remember, I just write it down here. X1 bar Z bar. Okay. Equal to X times Y plus Y bar. Okay. And then use the argument just now. Similarly, you can combine these two terms here. So you will left with Y bar Z bar. Okay. And then B, what do you have? B, so you could see that only these 2 blocks cover all the 1. So you need to minimize all these blocks. So for this block here, you will get 1 times Y bar. Can see it? Can see? Oh, okay. Okay. See some of you. If you can't see it, you can point out to let you see. Let you see. Okay, so and then you combine these two, you will get S bar times Z because they are differ in Y. Make sense? Make sense? Okay, make sense? Okay. See some of you nodding head. Okay, next. How about C here? Okay. How many blocks do you need to cover all these number? So you have 1 block, 2 blocks, and 3 blocks. Okay. But you can see that this one is essential. This one is also essential. So you need to include all these blocks in. Okay. And then you can reduce to this C here. So because 4 blocks, remember in 4 blocks in 3 variables will reduce to 1 literal. Okay. That's why all the terms here only have 1 literal. Okay. And then next here, okay, this one is more interesting. So you have 3 blocks here, right? Okay. So which block you need to take to cover this one? Okay. Let's say if I take this and this, is it enough to cover the one? No, right? Because this is not covered. Okay. If I take these two, this one is not covered. Okay. But does that mean that I need to take all of three of these or not? Should I take all of them? Should I take all of them? Should I take all of them? Yes or no? Should I take all of them to cover all the one? Yes or no? Yes or no? Huh? Should I take all of them? What do you think? Huh? What? Oh, must be no. Okay. So why no? Huh? Why no? Because if we take the top one and the bottom one, we also can cover the 4. So we want to take the least number of blocks to cover the 1. Okay. So if you include all of them, it will be too many. Okay. So you need to take the least number of blocks to cover all of them. Make sense? Make sense? Huh? Okay. So in essence, you need to care about this essential prime implicance. Essential prime implicance. Because this will help you to cover the one that's not covered by others first. Okay. After that, then you only consider the others. Make sense? Okay. Understand? Okay. So essential prime implicance very important. Okay. What's next? What's the time now? Okay, 5:39. Okay, next one is the 4 variable. So you can see that in 4 variable, we have 2 to the power 4, which is 16 blocks. Okay. So 16 blocks, you can have different combination of blocks. Okay. You also can have these corner blocks. Okay. Yeah. Because these are adjacent. Okay. Top and bottom is also adjacent. Okay. You can have corner blocks. You can have rectangular blocks. Okay. Different. And then you also can simplify them. Yeah, these are examples in your textbook. Yeah, the procedure is the same. Look at your expansion, build the care map, and then draw the block. Okay. So you can see that here, you can see that our block is always always even. We say even. Yeah, it's even 2 to the power n. Okay. So you can see that here we don't form a block 3 times 1 here. Okay, we always form a block 2 to the power m times 2 to the power n. Okay, makes sense. Because we only can combine x and x bar. We cannot combine x bar and y. Does it make sense, right? Only x and y bar, x and x bar will have the identity loss. Okay, so we can combine them. We cannot combine x bar y like that. Okay, so we only can build a block. Well, this one now. Okay. We can only build a block of 2 to the power m times 2 to the power n. Okay. For n in the natural number. Okay. In sense. Okay. Okay. So you will see that if we have 5, then we'll have, for example, 2 to the 5 is what? 32. 32. And then 64. And then 128. Okay. So you see that this cell is getting larger. Okay. So in that case, it will be harder and harder because you want to draw a large cell. Okay. So another way to encode this data is what we call the Queen-McCluskey method. Okay. So for n equal to greater than 4, this method will be easier. Okay. So what you do So what you do is you express each min term, okay? You express your min term using 1 and 0, string of 1 and 0 to see it. Okay. So you can put 1 as the I position if x occur, xi occur, or 0 if xi bar occur. Okay. So you encode xyz into position and 1 and 0. In that case, it's easier to see. Instead of looking at different alphabets. Okay? And then what you do is you determine all the products that you can form. Okay? All the n-1 variable product you can form by taking the Boolean sum of the min terms. And then you reduce one by one until the end. Okay? Okay. And then what you do is after you combine all the variables, okay, then you find all the Boolean product that's not used to form the product. Okay. And then you find the smaller set that sum up to the Boolean function. Okay, maybe you cannot imagine. Let me use this example here. And then I read the definition again. Okay. So first you get your midterm here. Okay. And then you can see that this is S1, S2, S3, right? Okay. So if X appear, you put 1. Okay. Y appear, you put 1. Z appear, you put 1. And then if Y bar appear, you put 0 at the Y position. Make sense? Yeah. So you do this for all this, all the midterm. Okay. This is the first step. So first step is this one. So you make the term become a big string. Next, you try to combine any two of them to produce n-1 product of n-1 variables. Okay. So you can see that 1 and 2 can be combined because they are differ by 1 literal. Right? Remember just now? Always remember this. This is the basic. And then 1 and 3 can also combine because they differ at 1 literal. Can see it? 1 literal, they differ. And then 2 and 4 differ by 1 literal. Okay, can combine. So you check for any two of them. Okay, so there's 1, 2, 1, 3, 2, 4, 3, 4, and 4, 5. Okay, can see it? Everyone can see it? Okay. And then after you combine them, right, you can replace the what do you call this? If the literal you already cancel it, you can just put a dash for it. Okay. For example, Y already get removed because you got Y and Y bar, right? So they are already combined, so you can put a dash here. Okay. And then next step, you combine again. If they are differ by 1 literal, you still can combine them. For example, 1, 2, 3, 4. Okay, they differ by you can form a block of 4 cells here. So you can combine them. Okay. Makes sense. So this 4 cell here, right, are adjacent in the plan map. What? Cannot see. Cannot see it. Yeah, I mean, can see or not? Okay, if you cannot see, right, how about look at these two first, okay? You can see that these two are differ in 1 literal, right? Okay, so when you combine these two, you get Z. But you combine these two that differ by 1 literal, they also get Z. Okay, so no matter how you combine, you still get Z. Okay, happy? Okay. Huh? Why? Yeah, what's question? What's the question? What's the problem? Huh? Last sentence. Oh, okay. So you can see that if you combine 1 and 4, okay, they are differ by 1 literal. Okay, so you can reduce SZ plus X bar Z into Z. If you combine YZ and Y bar Z, they are differ by one literal, you also can get Z. So anyhow, you only get Z. Make sense? 2Z is the same as 1Z. Okay. Yeah. Okay, so next one is you need to combine all the product that you haven't used to form a Boolean product. For example, this one you haven't used, and then this one you haven't used. Okay, these 4 you already used to produce the Z here, and then these 5 are used to produce 5 of them here. Okay, so the Boolean product that is not used to produce a new Boolean product is just Z and X bar Y bar. Can see or not? Can see it? You can see it? All these already used to build a new Boolean product here. And then 4 of these are used to build Boolean product here. So only left with this one and the last one. Okay. So you need to take these 2 and then compare with the original mean term here. So if what? If you see that this literal appears in the mean term, you should take a note, put a cross or what. And then you can see that X bar, Y bar appears in the mean term here. So you take a cross here. And then you take the sum of mean term that represent the function here. Okay. So this means when you take the sum of mean term here, you need to have cross in each column. Okay, maybe I think maybe you confuse again. So maybe look at this example here. So this example here got 7 mean terms here, okay? And then similarly, you do the big stream. Okay, you produce the big stream. So they are grouped by numbers of 1 here, okay? So that we can easily recognize the adjacent term, okay? And then similarly, you just combine, okay? Do all the combination you can, okay? And then you can see that there are only 4 mean term that is not used for produce new Boolean product. For example, this one, and then which one? And one here, and then this one. Where is it? Oh, this one. Okay, because 3, 5, 6, 7 are used to build the W bar Z, and then all the previous one are used to build the step 1. Okay, so and then you would put a cross if it is this literal appear as the this literal appears in the mean term. Okay, so you will put across. You can see that W bar Z is here, then W bar and Z, and W bar and Z. So you put across if the implicant, okay, appear inside the mean term. Okay, you will put across. Okay, so then the next thing is you decide which mean term to take. Okay, you need to take a minimum mean term to cover the function. Okay, meaning you need to have cross at every spot. So, but you will see that if you take all of them, you will take extra. Don't understand. Okay. Do you know how to build this table here? Anyone know how to build a table here? Okay. Up to here is it okay? Up to here. Up to here, okay. So how to build the table here? So these four implicants are obtained from this table here. Okay, the unused Boolean product. So how to put a cross here? So if you see that this implicant appear inside the min term, you will put a cross. Okay. So W bar Z is not in the first two, so there's no cross. But W bar Z is in here. W bar Z is in here. W bar Z is not in here. It's in here. It's in here. Okay, so you put a cross. Similarly, you do for WYZ bar. Okay, you can see that WYZ bar is in the midterm here, but WY here is Z. So there's nothing here. Okay, so you do it for all these implicants. And then the next one is you need to take the sum of implicants that represent this midterm expression, this Boolean expression here. Okay, so this means you need to have this cross. Okay, you need to have, when you take the sum of this min term, when you take the sum of these implicants, you need to have the cross. You need to have all the cross for the min term. Okay, the algorithm said find the smallest set of these Boolean products such that the sum of these products represent the Boolean function. So what does this mean? So this means that you need to have cross at every min term that appears in the Boolean function. Like this can understand? Cannot. Okay, step back again. so now the problem is decide. Okay, so now the problem is decide which implicant is in the sum. Okay, now the problem is this. So now how to decide? So the algorithm says find the smallest set of these Boolean product such that the sum of these product represents the Boolean function. So what do you mean by represent? What do you mean by represent? So what do you mean by represent here is you need to make sure when you take the sum, okay, you have to hit all the terms here. Okay, so how do you hit all the terms here? Meaning you need to have at least one cross under the terms here. A bit. Oh, so can understand now? Okay, but you can see that there's two choices here. Okay, you can take this one, okay, and then you can take this to fill out the empty here. You can take this tree to fill out all the empty slot, or you can take this two plus this one. Make sense? Right? So if you take this, you're left with 3 empty slots. Then you can take the second one to fill these 2 empty slots, and then you're left with one of this. So you can either take Wx bar y, or you can take x bar yz. Yes. Okay. Okay. So yeah. So this one is like what we call the essential implicants. Okay, essential implicants. These are essential implicants. And then these two are implicants. Okay. Okay. If that's the case, then Then we will stop here for the minimization of circuit. And then next week we'll do exercise on this part. This week will be on last week, so it's trees. If not, this is the last slide for the semester. Any more questions? No more questions? Last slide for this semester. Sure. Okay, if you still have if you still have okay, thank you, Ao Jing. So if you still have question, we still can deal with it next week on the minimization circuit part. This tutorial we will do trees, and before doing tutorial we will do a quiz. Maybe we will have let's put it 15 minutes first, okay? Although this is a 20 marks quiz. If we don't have enough time, we'll extend to 20 minutes. Okay? So before we start, let's go into break. We'll come back at 6:08. 6:08.图什么？图纸说第一个和第二个被好了。
是这个和这个看
对对对。
那这个呢？所以就是说，
没有，这一个要指这一个的往的最多，前一项的往的最多。
那这个往最方就是
1、2、3、4页。
这个叉
的叉。呀，这个叉就是如果这个 implicant 是存在在这个 min term 里，我就放一个叉。比如说，你看 WZ 它存在于这个里面，你看有 W8和 Z， 可是这里没有 W8和 Z。
OK，
可以吗？如果有存在，我就放一个叉。
是左边跟上面对应。
Yes。
它就是这样，那 D 呢
？D 是在。这个没有，这个我们没有缺。
对。
这个是就是
唯一的没被其他组合到最后的。
没有被组合，就是没有被 combine 的。你看这些被 combine 成这里了，所以我们不用这些了。
对。
然后这个你看这一个用了4、5、6、7来 combine，所以我们不用它，所以还没有被 combine 过就被用。
等一下，它不是要用 combine 的话，它应该是这一串要一样的。
如果要 combine 它，
是说这一串都是一样的，还是说是？
他们要相邻。比如说，你看，比如说这两个是相邻的。
就是。应该还有一位是。
Yes。
这个也是。
这个和这个。
和这个。
Yes， 没有错。
然后他们是。
你可以看到他们全部 combine 过后都是。就是这个。
OK。
那然后这个换完叉之后，换了叉之后，
然后你就要选这个 smaller step。
怎么选？
就是选 such that 你可以 cover， 就是你每一个下面都有一个叉，
就是选这4个里面选出来以后，让这每一个都有叉，
这一个下面都有一个叉，至少这个叉就够了。
会有很多种选法。
很大的话就有很多种选法。
那比如是不是可以？那
这个就有2种选法，
选这个或者选这个是？这两个加这个或加这个都。
就这个和这个的选。
那这个会有重复也不要紧，
不用紧，重复不用紧，但是你不可以就是你不可以选像这种，你不可以选这种。
这种正确性怎么证明？
什么叫正确性？
它为什么会是对的？
你说为什么是对的哈？这个应该是跟那个truth table 有关系
啊。觉得好悬啊。
没有不悬，只是说就是有点机械的，但是 呀，我们没有去说它为什么是对的，我们没有去证啊，应该没有很
这个丧是没什么特别意义的。
干是说它的
不知道
已经不在了，
不在。
就是它的那个
这个没有
literal 已经被吸收掉了，然后就
选的这4个呢，画在这里画一下，是哪个？
所以你
哪个
对，
没有画了，
这
4个，
是不是其实就是组合完以后要4位上都出现了空，
什么意思？
就横杠
啊，被吸收掉的那个就变成了一个横杠了。你看这个里面没有 s 跟没有 y 了嘛，所以 s 跟 y 就变干了。
那一定要这样先画下一步嘛？从这一步不可以直接到这个表，因为没有这里是吗？
什么意思？
做这个表格的意义要产生这里
啊，对，没有错。有系统的。要看完全部
我们自己看到有那个
啊，
我们要自己想哪个可以跟哪个 combine
啊，可是你们就可以用电脑了吗？对不对？
我们考试电脑
没有考试是没有啦，哎，我是讲现实啊，
我们考试不能用。
考试不能啊，考试不能哦。
这个01有什么用？
考试
没什么意义。
你的脑就是你的电脑。
这个01有用吗？如果不写这一列可以吗？
你可以不写其实，但是你写了过后就比较容易让你去查。不会吗？比较容易查。
它term是只会越来越少，对吗？
是会越
是为了 simplify 吗？
它不会这个比这个多。
很大应该是越来越少
啊，对，越来越少，越来越少。啊，对，越来越少。对的。
这个是指全部的还是
哪一个？
这个
啊，W8啊，这样 W8 是把这3、5、6、7 combine 的。我是全错了。我应该没有全错啊？什么？
所以这2个是不同方法去做还是？
哪一个？没有，一样的，没有。你要做这个 table 的时候，你肯定要有这个东西。
拿这个。
Yeah。
所以全错。
是我全错吗
？3、5、6、7。
对。有错吗？可是3、5、6、7不是这个3、5、6、7是他错还是我错？他错，应该他是4、5、6、7，不是3。他怎么不可能错？他错了。你看他用的是这个嘛，对不对？他讲。
他看这个，他用的是3、7吗？
哦，你讲他用这个号码哈。
Yeah，他用。
OK 啊，这样也没可能。可是 OK， 这样也没 sense。OK， 可以。可以，对。OK， 对，知道了吗？
前面有问题。
怎么问他没有？
什么？他先问。
OK， 你问。
那个前一个做。
前面一个。
那个圈画的好奇怪啊！一定要是长宽，一定要是2的整数。
2的倍数。
一定要2的倍数。
因为你不可能把那个 x8跟 y 加在一起。
我当时想问，这里为什么这个会不延过来一格？
啊，就是说它
就是因为它不能是3个。
对啊，没有意义啊。
懂，我现在懂。这个数的圈其实可以多余的。
多余的。
没用到其实。
它那个它不跟 connector 有关的，它有可能是，所以有可能是这个 它是 disconnector 有2个，把这个是 non-planar， 现在整个东西是 non-planar。
如果你把整个看成一个公式。什么意思？他说他的 graph 有2个 connector component， 一个 planar， 一个不 planar。
就是2个部分不连通。然后一个是立体的，一个是平面的。然后它不算平面图。
有立体图的东西吗？我没有介绍过。
我说的呀。
自己自创的。
语气在演示。
哪个？
怎么最后是选这4个？
因为剩下的他用了你是用这个来组这个，他用这个来组这个，所以这个是 simplify version 的4个，所以就拿simplify，所以他拿最 simplify 的 version 去做这个图。
对吗？
他 purpose 来 simplify。
对，那不是对，
那是什么我不可以拿来？
对的这样。
你可以 group 到没有问题。
老师这样，
你可以 combine。
你讲你不可以拿吗？
因为我们 two power of 4嘛，
然后
这样我们就是也有可能是4个这边，4个这边，对。哎，不是4个，就是类似。
你看到吗
OK 啊，
老师问个名字的问题，连接矩阵是不是有好几种叫？
我叫连接矩阵，
就是那个0101的那个。
解释器
图啊，A G，然后才能写上另外一个叫
另外一个是
这样子。
哦，那个2种是不同的东西
啊，那是有什么区别？
一个是 vertex 之间，一个是 H 跟 vertex。
老师
什么意思啊？
觉得叫你看全。
一个是点对点，一个是这个点连接了有哪些边
啊？对。XX 吧，来，你跟他解释啊。
分谁解释？
这个人，
他聊我。
他问那个3、5、6、7，怎么问4、5、6、7？
我刚解释了，因为他拿这边的号，他一开始的号码，他不是拿那个。
你问他听不听得到？
你问他听得到？
给他。
就他，
应该是。
不然你就要重新，
呀，
不然你就要重新写过 ，because it's take the because if you see the last four in step 1, they only use the
然后是什么？现在你觉得
这个是什么
？X
八
X 8等于1啊，因为它是
对不是？
对0。
Yes。
这太让我们班。
点快啊！以后没有以后了咯。
一节课
Is there something wrong？ 没有，他那个肚子痛，那个奥金。Is there something wrong? Is there something wrong? No, that session.
你不是去读书吗？
读什么？哦，要开始了。
简单。
不要说这个嘛。
对了，简单了啊。
有 proving，
有下雨。
一点点啊。
一点点。我就讲没有 proving。
Okay. I forget to pass the attendance list. 你要自己考？你要自己考？
要。
可是你不可以泄题哦。
要。
对，拜四就不用考。和奥金交。
在想歌。
想不到你吗？怎样？我要拍了哎！
正确，你看这个。
对，跟前状。online 啊 ，impossible。泄题给我。Okay, I put the attendance link right. Don't sign for your
No, Jaden, no.
Quiz. They also have to approach me to take the quiz.
难吗？我觉得。
啊？
难吗？
不会。那你现在要不要考？我要看。 要不要考？
刚才考
好啊，OK。不也是题啊？OK。Okay, so we got exchange. So Ao Jing cannot join, so instead Kok Fei join today. Okay. Okay, bye. You two can go. We'll be having quiz soon. They will be having quiz about 15 or 20 minutes. Okay, bye bye. Okay, as usual, we split into 4 groups. So the first person, please help me to count how many groups in your line. Okay, and then come and get the question paper from me. Please help me to count the first person in the group. Can you help count how many person in your group? Okay, final quiz.
22，
22。
是20。25，我忘记数第一19个。
25啊
，19。
放一下。你多少？
这是一样的，19分。
19。
这都是一样的。14个。14个。
25个。
19。
不对，我怎么没数到22个？
喂，
我不会数数了。
哎，不会数数啊。
给他。36、18、18加4，22、22。
19啊，一张吧。19啊。为什么都拿一个？你数啊，你现在就数啊。啊，现在就数。
因为
怕我就数吧。
17。
17。喂，夸张哎。来
18、
数，你14嘛，对不对？
对。
OK，你呢？
啊
你多少？19啊。
20、
22、14、18 OK。Okay, as usual, just take it first. Don't start yet. So, close your electronic devices. Face down your phone or your iPad. Don't start yet. Let everyone got it. First, you can read. Put down your name or your student ID. So this will be the final quiz. Oh yeah. Okay. So. Huh? 好一个。都是 22 or 23. Okay. I don't have mic anymore because I don't have the mic don't have battery that. So first part got 10 marks. Second part also got 10 marks, but got bonus 3. So the bonus can only add to the part 2. Okay. So bonus cannot exceed 10. And get it? So 10 front, 10 at the back. Bonus only add to the second page. Okay. So let's start now. Let's aim to stop at 6:32. 15 minutes. You need more time? 20 minutes past. Huh? Yes? 5 more minutes? Alright, clean up your solution. Check your name, student ID. And pass it to the front. Pass your answer to the front. Okay, pass to the front your solution. Pass it to the front. Please pass it to the front. Very good. One more. Go. Sorry. Good. Okay. 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 Hey, you guys，几时你们考试啊？你们几时考试？几点考试？哦，8点哈。Okay, so you guys have exam later, right? So okay. So next week, make sure you come back for the final exam marking. So last day you can ask for marks, and then please bring question next week if you don't know how to do any tutorial questions. Okay.
那个单词什么意思啊？
哪个单词？
最后两个单词都没。这个，
哎，这有教哎，
这什么啊？
那个 this number to color number。
为什么老师就不能多说2个字吗？然后这个
后面我，哎，有2个吗？一个 isomorphic，一个 homomorphic。
这个是什么
啊？
这个是什么？
还有一个，
还有一个是什么？
已经写2个字。
这个还有一个同组，
黑，
同黑就是几何，
不是这个，就同黑。那个是
啊，我好像只在题目里见到出现过，没出现，我都没仔细注意过。哎，那不对啊，老师
啊，
但是这个不是考了2遍吗？这里问最少染色体，这里又问是不是2分图？
对，
那我这里2分图说是2分图，那我这里是不是也认得是对？
也可以这样子做。
但是我这里写了6怎么办？我以为说面数。
哎，是，我都跟你说要学英语了，我都跟你说要看英语的书。
对那个顺来，我忘记了，最小的
是白跑菜吗？这个
是吧？
哦，如果是的话，它就你可以用它是白跑菜来说它是2，或者你就涂给我看它是。
我图给你，哎，对我是不是图给你看了？
我会画，
我画了图给你看了，但我这个写的是6，
那你要点给我看那个颜色，
我点给你看，
有点
我写 red blue。
OK，我看见。
OK，
是啊，
什么？
就是它第2个部分是按第1个部分的图来写。
对。
好
对。慢慢。哎，对不起，图片法看。
我什么都没有。
老师，我觉得下次可以考前出一个英语词汇库。
哎，这样啊？
会考哪些单词？
怎么办？
第2个部分没按第1个部分图来，自己搞
还没签，来，
怎么办？
怎么？
第2个部分没按第1个部分图来，自己搞了个图怎么办？
我看你怎么搞。
没有看到之前的那个 previous，就是完全按定义来自己用了一个举个例子啊什么的，然后是死掉了。
我要看一下你怎么写。对啊，怎么忽然间自己搞一个图来？
就我没有看到 previous，我就还当时很奇怪，就很多种可能嘛。
啊，
对，老师，还有路径的表示是怎么表示的？
那个路径的表，
就是我想表示一条路径，它不是要问什么路吗？